Hi, this is Professor Vinod Kumar, Department of Civil Engineering. I welcome you to my YouTube channel VK Civil Hub. In the last video, we saw two problems on stresses and strains with two practice questions. In today's video, we are going to see another two problems, problem number 3 and 4 with a set of practice questions. If you have not watched my previous video, I have given the description in the link. You can go there and watch it for your reference. Let's get into the video. Problem number 3 goes like this. A tensile test was conducted on a mild steel rod and the following data were obtained. Diameter of the steel rod 3 cm, gauge length of the rod 20 cm, that is the actual length. Load at elastic limit 250 kN. This elastic limit is already explained in my previous video. If you haven't watched it, please watch it. I have given the description. The extension at a load of 150 kN is 0.21 mm. That is, your delta L at 150 kN is 0.21 mm. Maximum load is equal to 380 kN. That is the final load. The total extension is given as 60 mm. After all the loads is given, this delta L becomes 60 mm. Diameter of rod at failure 2.25 centimeters. So these are all the given data, and we are asked to find Young's modulus, capital E, stress at elastic limit, that is sigma E, the percentage of elongation, and the percentage decrease in area. So in order to understand this problem, I have given a clear-cut diagram for you to understand the given problem. See, this is the diagram. It is a steel rod. The first part of the diagram shows you clearly it is a steel rod, and a load of 150 kN is given. Load will be actually starting from 0. Here at 150 kN, the delta L is given as 0.21 mm. And the next load is given as elastic load as 250 kN, and this is clearly based upon the Hooke's law. The second part of the diagram shows the steel rod after giving the load, that is at 380 kN maximum load. The change in length is given as 60 mm. That is, at the failure stage, the change in length is 60 mm. Okay, so you can clearly note that from the first diagram till the second diagram, there is a change in diameter, and beyond this 380 kN, the steel rod will suffer a failure. So now with this available data, we have to calculate the 4 values which is given in the problem. Let's see how we have to work out those. So the given data is diameter of the steel rod is 3 cm. We are converting it into 30 mm. That is the first part of the diagram, you have seen it. And the diameter of rod at failure stage, the diameter is getting decreased. So the D failure is given as 2.25 centimeters, which comes to 22.5 mm after conversion. Gauge length of the rod is given as 20 centimeter. We take as 200 mm. There are 3 loads given in the problem. One is 150 kN, that is 150 into 10 power 3 Newton. The load at elastic limit PE is 250 kN, that is 250 into 10 power 3 Newton. And the final load, that is the maximum load, is given as 380 kN, so it is 380 into 10 power 3 Newton. So with these 3 available loads, we have to calculate all those things which is asked in the question. And there are 2 extensions. At 150, the delta normal is 0.21 mm. Total extension delta L is 60 mm. Now let us see the first part of the question, that is to find the Young's modulus. Here we know that sigma is equal to P by A, that is load by area. The load is given, but don't get confused with the 3 loads. This is the normal stress. So the lowest load is to be taken, that is 150 kN. So if you substitute that here, it becomes 150 into 10 power 3 and divided by area. It is a circular rod, so the area is pi by 4 d square, where d is the diameter and the diameter is given as 30 mm. So pi by 4 into 30 square. So this value comes to 212.314 Newton per mm square. Next, the strain value, that is delta L by L. The delta L in the previous part is given as 0.21 and your L is 200 mm. So you're getting the strain value as 0.00105. Here the stress and strain has to be found, because to find the Young's modulus we want these two values, because that is the formula. E is equal to stress by strain, that is sigma by E. So your sigma value is found as 212.314 and the strain value is found as 0.00105. If you divide these two, we get 2.022 into 10 power 5 Newton per mm square. The second part of the problem is to find the stress at elastic limit. That is, in the diagram you would have seen the load given at elastic limit is 250 kilonewton. So that load has to be taken in the stress formula for calculating this stress at elastic limit. So again this sigma is equal to P by A becomes sigma E is equal to PE by A. That is load at elastic limit divided by the area. So likewise in the previous step, this load alone is getting changed. Instead of 150, here we are taking as 250. So 250 into 10 power 3 divided by pi by 4 into d square, that is 30 square. We are getting 353.67 Newton per mm square. So ultimately you can see the difference. At load 150 your stress was different and less than this one, and at 250 your stress value is higher. So as far as the load is increased, the stress value also increases. You have to make a note of this. Then the third part, percentage of elongation of the rod. In order to find that, the formula is percentage elongation is equal to total increase in length divided by the original length. That is given as gauge length in the problem. So that is your original length. Divide this and multiply by 100. So this is the formula to find the percentage of elongation. So your total increase in length, that is your delta L total, is 60 mm divided by original length is 200. 60 by 200 into 100 gives you 30%. Coming to the last portion of the problem, to find the percentage decrease in area of the rod. So this formula goes like this. The percentage decrease is equal to the original area minus area at failure. Original area is with diameter 30 mm and area at failure, the dia is getting reduced, no, 22.5, that we have to take. So pi by 4 into 30 square minus pi by 4 into 22.5 square will be your numerator, and the whole divided by the original area into 100 gives you the percentage decrease. So the whole divided original area, again we are dividing it, pi by 4 into 30 square and the whole thing multiplied by 100. So this is the value we are getting, 706.85 minus 397.61, the whole divided by 706.85 into 100, and this value we are getting as 43.75%. That is, the percentage decrease in area is 43.75. Let's check the results one by one, what we have worked out. We have found out Young's modulus E as 2.022 into 10 power 5 Newton per mm square. The stress at elastic limit we found to be sigma E is equal to 353.67 Newton per mm square. The percentage of elongation of rod we found as 30%, and the percentage decrease in area of the rod we found as 43.75%. So this is the final result of the given problem. Next we will see problem number 4. It is given as the ultimate stress for a hollow steel column which carries an axial load of 1.9 meganewton is 480 Newton per mm square. If the external diameter of the column is 200 mm, find the internal diameter, and the factor of safety is given as 4. So you have to understand this problem clearly. This is a hollow cylinder wherein the load is given. So as like the previous problem, just pi by 4 d square is not enough. We have to take the area of hollow section as pi by 4 into capital D square minus small d square. That is the difference between previous problem and this, where your capital D is your external diameter and small d is your internal diameter. So what are all the given data here? The ultimate stress sigma u is given as 480 Newton per mm square. There is no change for conversion. The load is given as 1.9 mega Newton. We convert as 1.9 into 10 power 6 Newton because mega value is 10 power 6. The external diameter capital D is given as 20 mm and the factor of safety is given as 4. So with these data we are going to find out the internal diameter of the hollow steel rod. In order to find that internal diameter, here in the problem ultimate stress is given. So with the ultimate stress we can't find the value, we have to find what is the working stress. So in the previous video I have explained working stress is equal to ultimate stress divided by the factor of safety. So the ultimate stress is given in this problem, factor of safety is given in this problem. With these data we are going to find out the working stress. So factor of safety is equal to ultimate stress by working stress, that is sigma u by sigma. That is 4 is equal to 480 divided by sigma. Here you can cross multiply and take the sigma to the other side. We get 480 by 4 as 120 Newton per mm square. So don't forget while working out these kind of problems, if ultimate stress is given, you have to convert it to working stress. So now let us check out how to find the internal diameter. We know that the sigma value is P by A, and this sigma which we found out in the previous step, that is the working stress, 120 should be taken and that is equal to P by A. So 120 is equal to 1.9 into 10 power 6 divided by A. So here I have already told you this is a hollow steel rod, so the area formula becomes pi by 4 into capital D square minus small d square. Here you have to apply this. With this formula we know the value for capital D, substitute it, and from this we can find out the small d. So ultimately what happens, if you take this capital D square minus small d square to the other side, it becomes 200 square minus d square is equal to 1.9 into 10 power 6 into 4 divided by 120 into pi. So from this the next step is d square is equal to 200 square minus 20,159.62. So this value is 19,840.38. And if we take the square root on both sides, we will get the value of D as 140.85 mm. So the result is the internal diameter D is equal to 140.85 mm. Here there is a practice question for you to work out based on the previous two problems. The problem given is hollow steel column. Sigma is given as 125 meganewton per meter square. Capital D, that is the external diameter, is given as 30 centimeters. Load P is given as 2.1 into 10 power 3 kilonewton. And here you have to find the internal diameter small d. I'll give you the hint for you to work out. First, convert all the units to Newton and mm. Then use the stress formula sigma is equal to P by A. And for that A, substitute pi by 4 into d square minus, that is capital D square minus small d square. That is the then cross multiply and find the internal diameter. For this practice question the answer is D is equal to 261.93 mm. If you want you can repeat the video and check it out, work out to get practiced. If you like this video, kindly subscribe to my channel VK Civil Hub, or you can contact me through vinodkucivil@gmail.com. Thank you. Let's meet in the next video.